The top happiest jobs revealed. So look who's there in the middle. It's a Java developer. The idea here is that if you want to be happy, go and write code in Java. But apparently you are in the wrong room today because we'll be talking about .NET collections. Hello everyone, thanks for coming. I'm happy to be here with you today and talk about things I love and enjoy doing. Before we jump into it, we've got an app called SSW Rewards. It's written in .NET MAUI and we use it for conferences and user groups. So you can earn points there and exchange them for nice things, t-shirts, cups, and even discounts on our events. So I work with SSW for a couple of years already, and I've been coding for over the last 15 years, and 10 years of those was commercial experience. I worked with different technologies, and my all-time favorite one was always .NET. I started with .NET Framework 4.0 when we didn't have things like async await, tuples, string interpolation, pattern matching, and many other nice things. And it's really fascinating to see how the platform evolved since then. I also run a competitive programming club in Newcastle. It's a small group, but we meet regularly every week for the last 3 or 4 years. So if you happen to be in Newcastle, feel free to join. Just shoot me a message. Before we jump into the topic, I also want to share a piece of news which I came across a couple of weeks ago. Originally, it was published by six months ago, but it was republished by Channel 9, and it was about the top happiest jobs revealed. So look who's there in the middle. It's a Java developer. It's not just a developer, it's Java developer. Well, I find that's funny, because if you have a look at the .NET Link code, which is nice and tidy, and then you look at Java Stream API, which is very wordy, can you feel happiness flowing through your body? Well, not in my case, to be honest. So the idea here is that if you want to be happy, go and write code in Java. But apparently you are in the wrong room today because we'll be talking about .NET collections. So we refresh some information first, and then we move and look at the arrays, lists, queries, and dictionaries. I think that most of you use those collections in your code, and sometimes it's very useful to see and know what's happening under the hood, to understand how you can make your code more performant and avoid doing stupid things. So before looking at specific collections, let's talk about algorithms in general. What we need to know is how are we going to compare one algorithm with another? Which one is better? So scientists ended up with two main approaches. The first one is called random access machine. The idea here is that you count the number of steps required for algorithm to finish, and you compare algorithms based on that. That's a very simplistic approach, but sometimes it can be useful because when you know the number of steps, you know how fast your CPU is, so you can kind of guess how much time it will take for an algorithm to finish. But there is another way, which you're probably familiar with. which is called asymptotic analysis. You probably heard about big O notation and a couple of others, which we won't be covering in this talk. And that big O notation is expressed in functions. Here we have a chart. We've got input size over the x-axis and time over the y-axis. So if we have a function which is constant, then it will look like this. So it's going to be just straight or kind of straight horizontal line. That means that whatever input we pass to our algorithm, the time is going to stay kind of the same. There is another function, logarithmic. So you see that this function is actually, it actually grows over time, so with input. Then we have another function which grows even faster, that's linear. And the time grows proportionally to the input size. And then we have a bunch of others, but we'll look at the square function. So it means that every time you increase the input, the time increases square of that. There are others like cubic functions and exponential functions, but we definitely don't want to have those in our algorithms because that will be very slow. Okay, so guys, you might say that this is all theory, it's boring, but how can I look at the code and say, well, you know, this code will take, let's say, linear time to complete? Can you guess, like, what I will see in the code for a linear function, big O of n? Any ideas? We've got a hand here.
Loops.
Right. How many?
How many loops?
Yes.
One.
Cool. Yeah, it actually can be several because in asymptotic notation you can drop the constant. So if it's not nested loops, so it still will be linear complexity. All right, how about n square? What will I see in the code?
Lewis. Out of nested loop.
Right, so that's a nested loop. How about the constant?
Return constant. Getting
Cool.
the first element of an array.
Yeah, maybe. So
Next one,
yeah, the idea here is that you do not go through the input. So you just return maybe a cached value, or you can just quickly get it somehow. All right, how about logarithm?
Binary search.
Cool.
Nice.
Yeah, binary search. And the idea there is that you also don't go through the entire input. So you always divide somehow. In case of binary search, you divide it by 2. Nice. So now quick refresher of the interfaces. In dotnet, we've got IEnumerable, which is one of the base interfaces, and it doesn't allow you to do much except just iterate over a collection. But if a collection implements IEnumerable, that means that it can be queried by link. Then we have another interface, iCollection, which inherits from IEnumerable. It allows you to do more things. It allows you add and remove elements from collection and get some internal state like count, which you can't get, by the way, in IEnumerable. Then we have iList, which allows you to insert elements and remove at certain position or get index of an element. Then we have iDictionary, which inherits from iCollection, and it provides functionality for working with dictionaries like get value, get key, try get value, so on and so forth. Then we have iSet, which provides functionality for sets, and iRead-only collection. This is a base interface for more specific interfaces like iRead-only list, iRead-only dictionary, and iRead-only set. All right, so one of the purposes of this talk not only show you some performance tips and tricks and what to do and what not to do, but actually encourage you to go and look at the source code of .NET Runtime and look at the source code of collections which you are using every day. So where do I find the code? You open GitHub, go find .NET Runtime, and then you see folder. Inside that you will see libraries folder, and you start scrolling and you see familiar folder names like system.collections. You open it, you go inside, and you see more familiar names there, system.collections.generic. You open that folder, and you see there only like a dozen of classes. You'll see stack, linked list, but you won't see list, dictionary, or queue there. Where are they? They're actually in another folder called system.private.colib. And this folder contains lots of things, including lists, dictionary, queues, and other collections. That was done to avoid circular dependencies. So many collections, they were moved from system collection to system.private.colib. All right, now let's talk about arrays. So when you start learning programming, I think arrays are among the first things which you work with. And in .NET, they are reference types, because you don't want to copy like a huge array every time when you pass it to a method. And .NET Runtime has a class called array, which is an abstract class, but it can't be implemented. If you try to implement it in your code, you'll get an exception. So it's only for internal use. Same exception you will get if you try to inherit from classes like system.enum, system.valueType, system.delegate. So they are not for you to implement. The number of elements in array is roughly 4 billion and 2 billion per dimension. Yeah, I have no idea who would have reached that limit. Yeah. So the maximum size is 2 gigabytes, and this is a restriction which comes from the garbage collector. This is the maximum size of object, but you can change it. You can update the flag called GC allow very large objects, and then you'll be able to go over that limit. And now the most important part here is that arrays, they store data as a contiguous block of memory. That means that all your elements in your array, they are stored next to each other, and it's very quickly to go through them and access them. Let's look how quick it is and what happens if you don't do it. So we have a method which we'll be benchmarking here, and we have a table which is a two-dimensional array, 1000 by 1000 elements. And what we do, we just iterate over it row by row. So we assign some values, but it doesn't really matter. And we have another method which is very similar, but this time we swapped the indexes and we go column by column. Which one do you think will be faster? The one which goes by rows or by columns? Any guesses here? It's 50-50% chance.
Columns.
Okay, we've got columns. Okay, by rows.
C++.
There is no such answer. Yeah.
Access directly by pointer. What's the answer?
Okay, the answer is by rows. And this happens because elements are stored next to each other. Let's have a look at the benchmark results. We've got 1000 elements. It was run on my Mac machine, so it has 14 cores, and I've got .NET 8 installed. So you can see that the results are kind of the same, so it's only like 6% difference, which is not that big. But if we do it for 10,000 elements, then suddenly you see that it's 4.5 times slower. And that happens because your memory is actually read not element by element. So it's read in chunks, and those chunks, they can be cached in CPU. So if you have a number of elements cached in CPU, it means that you don't have to go every time to memory and read it again and again. And iterating rows by rows allows us to do it. So it's all done automatically behind the scenes. You don't need to do anything. CPU does that, but you need to just iterate in the right way. .NET Runtime has not only multi-dimensional arrays, but also jugged arrays. So a jugged array, this is an array of arrays. Let's have a look what happens if instead of two-dimensional array, we will use a jugged array. So now we have, again, 1000 by 1000 elements. I omitted some initialization logic, and we iterate by rows, and we also iterate by columns. Again, only indexes were switched. Now let's look at the results. Same machine, same thing. Now, for 1000 elements, we've got 43%. And for when you iterate for 10,000 elements, it's like 8 times slower. This is again all how your arrays are stored in memory. I also mentioned about the 4 billion limit. Has anyone here actually ever exceeded that number or hit that limit? Costa, have you ever? No, never. You know, actually, I exceeded it when I was preparing for this talk, and I didn't expect it. So I had a great time. I was benchmarking, everything was good, it was fun, and then suddenly my benchmarks started to fail at runtime with out-of-memory exception. So I tried to figure out what I've done, and I noticed that I changed the initialization of array from whatever number it was to 100,000 by 100,000. But, you know, it's still much less than 4 billion items. Is it? The thing is that multi-dimensional arrays, they are still stored as a consecutive chunk of memory. So we open ECMAScript 335, and in the paragraph 891, we find the following. An array type shall be defined by specifying the element type of the array by ranking number of dimensions of the array. So you see, it means that multi-dimensional array is still an array. And then the next paragraph says array elements shall be laid out within the array object in row major order. So it kind of means that it forms one row in memory. The elements associated with rightmost array dimension shall be laid out contiguously from lowest to highest index. That means that still the indexes, they've got to grow in the most nested dimension which you use. So what happened? I changed the size, and now we've got 100,000 by 100,000 elements, which is 10 billion. So this is definitely much more than 4 billion. But not only that was a problem. If we calculate how much memory that would take, this is 10 billion multiplied by 4 bytes. This is the size of an integer. And we get roughly 37 gigs. So it's more than on my machine. So, and we also exceeded the limit in 2 GB per object and per array. All right. Yeah, we've got a question.
Found about the garbage collector flag.
No, I knew.
Problem with find the
No, I knew about it before. Actually, I didn't check it. Didn't use it that time. All right. I should have asked this question in the very beginning, but let's do it right now. What is the first index of an array in .NET? Like when you get the first element, what index will it be? Yeah.
Where's it? A?
So 0. So does anybody write code in Rust? 1? No? No?
It's Rust 1 based.
I think so. Yeah, if I remember it correctly. So the answer is it depends. And it depends on how that array was created. If you used the traditional native syntax, then everything is fine. No problem here. But .NET also has that nasty class array. And if you use the create instance method there, it allows you to pass the type of the array. It allows you to pass the length, which is 3 in our case, and the starting index, which is -5 in this case. So we can set a value to index -5, then we can read from it. And if we try to get an element, let's say by index 0, we get out of index out of range exception. And if you try to cast this array to like a normal array, then it will be an invalid cast unless the index starts with 0. This is something like a funny thing to know about, but hopefully you are not using the array class because you don't need to. Several take-home lessons for arrays. Sequential memory access is always faster than random access. So arrays are stored as a contiguous chunk of memory, so it's faster to read through it. It will be cached, and it will increase your performance significantly. So that's something to remember about. Another thing, multi-dimensional arrays, they're also arrays, and they are also stored as a contiguous chunk of memory. So it's easy to forget, especially if you've got like multiple dimensions. The next one, you don't need to use the abstract array class except for static methods. So that class has useful static methods like binary search and some others, but you don't need to initialize an array using that class. And be careful if somehow you have it in your code. For example, an old library returns it. You don't have control over it. Be careful with the lower bound because it cannot be 0. All right, let's move on. Now we'll talk about lists. So list is a data structure which allows you dynamically add and remove elements. But internally, it also uses an array. It means that all restrictions which are applied to arrays, like limits and so on and so forth, they also apply to lists. That collection has several important internal properties. The first one is size, which you access using the length and count properties. The next one is version. So every time you update your collection, it will increment the version, and that variable is used by methods like move next and for each, so that the collection is not updated when you're iterating through it. If that happens, then an exception will be thrown. And the next one, the most important property, is capacity. What is capacity? This is the size of that underlying array. How many times did you see that code? When you get some DTOs, and then you want to map it to your domain object. So you just create a list, then you iterate through a list of your domain objects, and you add them just one by one and return the result. What's the problem here? The problem here that on the second line, we are not passing the capacity. And by default, the capacity is 0. Then when you add your first element, it's increased to 4. And after that, it's doubled every time. So while you are adding those elements, your internal array is increased every time. So let's say you have 4 elements, and then you want to add a 5th one. You can't do it with arrays. You need to allocate them in advance. So you create .NET Runtime creates another array which is twice as big, copies all the elements to the new one, and then adds the element. That means that first of all, you are wasting CPU on copying, and second, you might be wasting memory, because those old arrays, they're still hanging out, they're in the heap, and when they will be garbage collected, no one knows. Yep, we've got a question.
So does that mean it's O of 1 when you have free capacity just by calling add, but then it's O of n when it has to reallocate the array?
Yeah, absolutely. So the note was that, is it true that when you add an element and you have capacity, it will be O of 1? And when you don't have capacity, it's going to be O of n, because you need to iterate through all of the elements and copy them. So the answer is yes, it's absolutely right. And that's the main problem with lists. So that's why list constructor has a parameter called capacity. All right, now let's look how bad it is. So we've got a couple of benchmarks here. We instantiate an array of, a list with 100 elements, 1,000, and then 10,000 elements. And to one list we pass capacity, and we are not passing it to the other. So we see that for small arrays, so it's much slower for small arrays. It's like 30% for 100, 10% for 1,000, and 21% for 10,000. And yeah, as it was mentioned, the add method in this case might turn from a constant time to big O of n. Getting an element from a list, it will be always constant time.
What's worse than that, right? It's O of n times by however many times you have to reallocate.
Yes, 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 it's exactly that. All right. Take-home lessons. So always pre-allocate capacity if you know it. If you don't, then just make a guess. Make a guess, and in many cases, you can make that guess pretty reliably. For example, you have 500 employees in your company, so you know that it can't grow, for example, faster than 50 employees a year. So allocate, 750, 800, 1,000, and then you won't be wasting memory and CPU. But quite often you know exactly the capacity, like in that example when you map one list to another. So based on what I said, it means that removing items can be costly, because the underlying structure is what? This is an array. And you can't have holes in an array. If you remove the very first element, it means that you need to fill that gap, and you need to go through every element and move them. the list has a method called clear, and it doesn't reset the capacity. Clear only removes the element from that array. So if you added 100 elements, then you remove them all, the underlying array will still be of that size. Sometimes it's useful if you want to, if you know that in the future you might again add like 100 elements or so. But if you know for sure that it won't be that big, then you are wasting memory. So for that reason, there is another method called trim excess, and it will reduce capacity. But it will only take effect if the size of your list is 90% of the capacity. So if you have 100 elements, 100 element size of your array, and only 95 elements in your list, you call trim excess, nothing happens. But if you've got 89 elements in your list, then the capacity will be decreased. All right, let's move forward to queue. Queue is a first in, first out collection, and internally it uses, again, an array and 2 pointers. Same as with list, clear doesn't reset the capacity. Let's look how it works. So we've got an array of, let's say, 4, for example, and we have 2 pointers, head and tail. They both point to the first element, and head is on the left in the beginning, and tail is on the right at the end. So we add elements, and our tail pointer moves to the right. So we added 3 elements, and now we start removing them. In this case, our head pointer moves also to the right. So we remove 2 elements, and now we want to add again. What happens? We add another element, and now our pointer needs to point somewhere, but we don't have elements in our array. What should we do? Probably we need to increase the capacity. So when again, like copy, allocate a bigger array, and then copy all the elements. But we would be wasting those slots in the very beginning on the left. So how can we overcome this problem? We just swap head and tail. So now tail is on the left and head is on the right. And the same story continues. When we add an element, tail moves to the right, and again, until we use all the elements in our array. And now, if we need to add a new, another element, then we need to allocate a bigger array. But head and tail is reshuffled back. So now head is on the left and tail is on the right. We set the pointers, and then we just copy all the elements to our new array. And then add the next item. Cool. All right, now let's talk about dictionaries. Has anyone ever used the dictionary in their code? Okay, we've got a couple of hands, more than a couple. Awesome. So has anyone actually looked under the hood what's going on there and how it's implemented? Was it a hand? No? No? Okay. Yeah, you didn't use it, but you looked what's going on inside. So actually, dictionary is a data structure which allows us very quickly get elements. And it's based on a hash function. So inside dictionary, we've got 2 main arrays. They are called entries and buckets. We also have a private data structure, a private struct called entry. It has 4 properties: key value, hash code, and next. So next is a pointer to another entry. As you might know, hash functions they are not perfect, so they might generate collisions. Collision is a situation when different inputs, they produce the same output. So in this case, we need to handle it somehow. In all dictionaries, they are designed with that in mind, that collisions will happen. We just need to properly handle them. And that next property is actually to point to the next colliding element. Ideally, we don't want to have collisions, and if there is no collision, then the so values of next, they are kind of encoded, so there are special meanings. If it's 0 and greater, that means that we are pointing to a colliding element. If it's -1, it means it's an end of that chain of colliding elements. If it's -2, it means that's the end of empty element. And -3 and lower means that this is a chain of empty elements which you can use. That's a bit advanced. We won't be covering it in this talk, but we'll have a look how these internals work. And there is another array called buckets, which stores virtual indexes of entry. So basically, this is your index, which points where the element is stored in the entries array. What that I'll explain in a second. All right, so now we have two arrays on the right, buckets and entries. We have our code on the left, top left. Dictionary has integer as keys and strings as values. What happens when you add an element? For example, we will be adding element with key 305, and the string is going to be apple. So we'll be adding fruits today. When you add in first element, those buckets and entries arrays, they initialized. And then to save it, you need to get the hash code of the key. For integers, it's easy. So hash code is the same as the integer. In our case, it's 301. All right, now we need to figure out the index of the bucket, where we're going to put it. It's calculated as the hash code divided by the length of the buckets array, and we take the remainder. So in our case, it's 1. Then we get the bucket by reference. So it means that if we update the variable, the element in the array will be updated. That's important. Then we get target index from the entries array. OK, now we've got the buckets index, and now where we're going to store it in the entries? It's easy. So we will store it, one by one, and the target index is going to be count. This is what happens when your dictionary is empty, and if you didn't remove any elements from it, it will just fill the entries element one by one. And if you, let's say, print the content of your dictionary in the console, you'll see that it will be in the order you added the elements. And now we get that entry by reference. So we update that entry. We set those keys like those properties like value, next, that -1 is next. It means that there are no collisions. And we store virtual index in the bucket. So now our bucket points to our entry. I think at that point you probably realized why we store virtual indexes, because 0 is meaningful. So it would be pointing, to the 0 entry in the entries array. But we don't want to do it. 0, in our case, that means empty. Nothing is stored. OK, Now let's add another element. We do exactly the same steps. We get the hash code. In our case, it's the same as integer. We get the bucket by reference. We find the target index and target element in our entries. So this is count. Currently, we have one element, apple. So our index is going to be 1. And we increment the count, by the way. Yeah. Then we get entry by reference, and we update hash code, key value, and set next, which will be -1 in this case. And we update the bucket. OK. So now we've got 2 elements in our dictionary. And actually, those variable names, they were taken from the source code. So if you have a look at the source code of dictionary, you will be able to find that logic very easily there. But now let's add an element with a collision. So orange will have will have key 602. We get hash code. We get the bucket. Yeah, and by the way, you see that the bucket will be 2. So it's not empty. We know it. Bucket with index 2 points to lime. We get the target entry, which is just sequential. We update it. And now our orange points to lime, to the colliding entry. What we need to do, we need to update our bucket so that it points to orange. So you see, we kind of created that chain of elements. Ideally, we want every bucket to point just to one entry. But if a collision happens, then we start forming that chain of entries. Take-home lessons for dictionary. Dictionary performance equal to the quality of your hash function. If it's bad, then the performance of your dictionary is bad. It means that every time we get an element, we need to go through the whole chain of entries. Capacity is changed by doubling, similar to lists, but it rounds up to the nearest prime number. That was done so that the number of collisions is minimized. And you see prime in quotes because some prime numbers, they are located next to each other, like 5 and 7, 11, 13. So we don't want to hit one of those. That's why some prime numbers, they are omitted. Again, clear method doesn't reset the capacity. There is trim access. And resize might trigger rehashing of every element if the number of collisions is 100. So calculating of the hash is the most time-consuming operation in dictionary. If it takes long, then suddenly you get a performance degradation. And complexity, so technically, in most cases, it will be big O of 1, constant, but worst case is when you've got lots of collisions, it's going to be linear, big O of n. All right, so we are done with the basic stuff. I think it's time to move to more advanced things like thread safety, concurrent dictionary, concurrent queue, concurrent stack, concurrent bag, and I produce a consumer collection. But it's all will happen next time. So today we have a form to fill. It's a feedback form. So if you do it, you'll get 800 points in our SSW Rewards app. So, and yeah, here's the link. Thanks for joining us today.
Wow.
right. Do we have any questions?
Yes, we
people.
do. So
awesome.
I'm going to come stand up here
Yep.
so you can see. That was a great talk, man.
Thank you.
I want to say that not enough .NET developers really care too much about what's actually happening under all of these really great tools and classes and functions that the runtime gives us.
Yep.
And yeah, it's not until you sort of start dealing with lower level languages that you suddenly realize all of these performance gains that can be there.
Yeah.
And it just doesn't occur to a lot of people in these higher level languages,
Yeah.
right? So I think it's a really good thing to sort of bring some visibility to that. Sort of take away some of the mystery of how these classes and collections that we use every day actually work under the hood.
And it's very convenient to use them.
Yeah, it really is. We actually got a really good question. If you want to bounce back to your dictionary slide.
Yep, which one?
That one there. So we had a great question from online, which is, what if the head is occupied? So if someone tries to do dict.add with 601 as the key,
Yeah.
what happens there? Do you want to walk through that scenario?
If the head is occupied,
So let's just walk through if you were trying to add a new
601.
record with 601.
yeah. Okay, so in this case, we'll have, again, a collision because the reminder will be 1. Same for Apple. So in that case, the bucket will already be set. So we will need to increase the capacity of buckets and entries, to accommodate the elements. So, and then but let's say that we are not resizing in this case. Imagine that we've got the space. So in this case, it will be exactly the same as it was with the orange. So the entry will be stored in the entries array, and our bucket will be pointing to the element which has just been saved. So and then whatever element you added will be pointing to Apple that this is the next element in the chain. It means that we will have like 2 chains, one with orange and lime, and another with Apple and whatever element was added.
Okay.
Yeah.
So it's not going to blow up. Essentially, it'll handle it just fine. Yeah. That's excellent. And so I had a question, which was coming back to your sort of upper threshold with arrays, right?
Yeah.
The dictionary under the hood is still just a couple of arrays. So we still have to be concerned about maximum number of elements, etc.
Yeah, absolutely.
Do you find any sort of use cases where if you know your dictionary is going to be beyond a certain size, you will pay particular attention to what type of key you're using? So I'm thinking, strings, you can have collisions quite frequently, right? Do you kind of have a rule of thumb of your own where you might say, I can get away with having a string as a key for this particular dictionary? Sure.
Yeah.
There you go.
Yeah.
Okay. Or do you have like a rule of thumb where you will just always try and use an integer as a key for dictionaries?
Well,
what's your strategy for that?
Well, quite often it's dictated by the business. What's the problem you're trying to solve. So, and then you kind of have to figure out whether the hash function returns the values like good enough for a performant dictionary. So if it's good, then use the key which you're using. If no, then try to find either something else or hash function which just returns you better results.
So it's a big fat, it depends, basically.
Yeah.
Like pretty much everything.
Yeah.
Right.
Yeah.
Okay.
Yeah. And by the way, dictionary also has capacity. So you need to, I forgot to mention it. Yeah, you need to pass the capacity.
Oh, so you can still initialize a dictionary like you can with any, like a list by giving it an initial capacity. Yeah?
Yeah.
Excellent. Okay, well, I think that is all the questions that I've got for you today. Oh, we have some from the actual crowd. Yes.
Do have one. So you said before that the keys are hashed and stored in the bucket, right?
Yeah.
To store them. So how does it work then when we try to retrieve that item? Because it needs to hash our key. And if there's a collision, how does it know which of the two items?
Yeah, that's a good question. So actually,
Do you want to repeat that question?
yeah. So the question is, how does it know that which element you want to get from a dictionary if there is a collision? Because hash will be the same. So you compare them by the key. Also, you not only compare them by hash code, you also compare elements by the key in that collision chain. Yeah, it's not on that slide.
I'm just wondering if we...
Yeah.
Where did you have your struct? Somewhere there.
Yeah,
There you go.
yeah,
So it does store the key inside
Yeah.
of that struct that you can compare against.
yeah. Good question.
Excellent. All right. I think I can let you get out of here. This was Anton's first ever SSW user group as well, guys. So yeah, good job.
Thank you.
Excellent. Sign us off, man.
Yeah,
Go on.
appreciate it.
This has been Anton.
Signing off for SSW TV.
Great.